I'll introduce the other thing that I wish to speak about from Langmuir's lecture. Okay, and not only from Langmuir's lecture, I've also read a number of Langmuir's original papers. And so partly it is from his Nobel lecture and partly from the papers. Langmuir actually uh, also played a phenomenal role, a seminal role in understanding the behavior of insoluble things like oils, etc., which how do they behave on the surfaces, okay, and surfactants, and that must have had something to do partly with the because we know that the Gibbs equation already had explained how exactly the surface tension gets lowered. Okay, and but that's not all. There were many other experimental pieces of work, which were done long before Langmuir. Okay, the first perhaps is these two people, Pliny and Benjamin Franklin. Okay, and they had done a remarkable experiment. I think in the probably in the early part of the 19th century or in the 18th century, or maybe, yeah, can't remember the date. But what they did was, they spread a bit of oil, on a lake, okay? And they found that the lake is like becomes like a mirror. It was glistening, okay? And obviously, and they put a very small quantity in, and so it was very clear that it was spreading, over the water. Okay? Now, then came this person, Fraulein Pockels, a schoolgirl, right? And for those of us, I think, for me, Fraulein Pockel is probably the best example of how we could have done extremely creative things during the pandemic, in our house, if we were smart enough, you know, if if we were smart enough to do many things, you could have done so many things with whatever you got there. And so, what was Fraulein Pockels doing? Yeah. And I will send you her paper published in Nature, okay, which was communicated by Lord Rayleigh. Okay, I'll send you after the lectures today. Okay, so Pockels, was doing a very interesting experiment, and partly it was also because Lord Rayleigh himself had done some very path-breaking work, basically borrowing on the ideas of Benjamin Franklin and Pliny, and so what happened was she was making waters, water surfaces contaminated with different kinds of contaminants. Okay? And, she was just at that. Now, then she did a remarkable experiment. What she did was she put some tin strips, very must be very fine tin strips, which just kind of floated on the water, okay, and used those strips to squeeze the surface. So she was bringing them closer together, or taking them apart. Okay. Now, what happened was that when she was doing this, okay, so the if these contaminated molecules on the surface were getting concentrated, as she was shifting the barrier, okay, and because of that, between the two sides, the one side where she was taking the strip away from, and the side on which she was towards which she was moving the strip, the surface tensions were different. So it was creating a balancing force, which she could measure. Okay. Second, she could, she put the way she was measuring, determining surface tension was that she was putting a very thin, small coin, on the water, okay, and which effectively, on that you can keep adding some weight which she could do, and basically from the how much weight you require for the disc to finally break the surface, you can measure the surface tension. So that's the kind of thing she was doing at home. And she was doing it because apparently, I think her grandmother or mother, somebody was unwell and she did not want to leave them and go to college or school or something. So she decided to be at home and, perform these experiments, incredible person. Okay. And then, of course, Lord Rayleigh studied castor oil, the spreading. Okay. And he'd also found things which are very similar to what Benjamin Franklin, etc., had found. So it is not as if Langmuir, did not know all this. Okay? All this was prior art. You can see 1899, 1891. Okay? Whereas Langmuir's work on these things started around 1910, 12, maybe a bit later than that. Okay, so that was very, very profound. We of course talked about the work on tungsten, which was very, very important, and how through his cleanup studies he came up with very path-breaking understanding of the interactions that take place on the surface. Uh, Now, another, and as I told you, I mean, there are many things in his Nobel lecture, and it's not possible to cover all. But one of the things I thought I will tell you about, which I started telling you about the work of Pockels and Lord Rayleigh, was the work on having contaminants on the surface of water. It need not be water; it could be some other fluid. Okay? And what basically was, as I said, I mean, it was known even, and that was one of the reasons for the Gibbs equation, that it was known that many times, if you add things on the surface, there are things that form, and that lowers the surface tension. Okay. No, and that has been always a very important area and of understanding that how exactly do these molecules actually stack up on the surface? What do they do? And while some of these very phenomenological understanding of compressing the trough, the way Pockels had done, and that was known, and that affects the surface tension. But there was no very deep understanding at that time, and that is where Langmuir came in, because Langmuir was really good at that. He could really get to the bottom of phenomenological findings. So, what was known from Pockels' work was that when you compress these things, you slide the that tin sheet, and one side gets compressed and the other side gets expanded. And so, what Langmuir thought is that obviously, is there a possibility that there is some kind of change in the state of matter on the surface as a result of these kinds of things? And is it that certain things spontaneously exist, like let's say in the solid state or gaseous state or liquid state? So we know no, there's so many compounds which are automatically solids. They will form. Some are liquids, some are gases. Okay, at the particular temperature at which you're studying. Yeah. So, and what you'll see is, like for example, we know that Van 't Hoff, for example, was able to apply the gas equation to understand osmotic phenomenon. Okay, and what did he do? He just basically used a similar kind of an equation, where he said it's pi v is equal to CRT, and where pi is the osmotic pressure. So really drawing analogy from PV is equal to nRT. Okay, I mean that's what these people were very good at, trying to draw analogies. And similarly, Langmuir asked that can it be that actually on a surface all you have is a two-dimensional gas equation, and so by analogy, he kind of wrote pi a is equal to nkt. Okay, and so and you can see, I mean, all he has done is change volume to area. Okay, and then in fact, I took these slides from the classes lectures I used to give in IIT Bombay, and just dug them out from my notebook. Okay, and this is really from not from the Nobel lecture, you may not find it, but there are certain papers, seminal papers that Langmuir wrote. Okay? And I'll pass on a few of those papers to you. Okay? And so what basically Langmuir kind of picturized is that actually what you have is that in an uncompressed state, many of these molecules which contaminate a surface, okay, are present in very loosely kind of present on a surface, okay, very sparsely occupying the surface, so it would be something like that. And what Miss Pockels had done was really by squeezing, they were just being brought closer together, you know so you can imagine that this is like a gas state, okay, and this is like a liquid state. Okay, there's a little more higher density and relatively greater order. Okay, and if you now and these were what they were studying was surfactant molecules. Okay, so we know that a surfactant has a long tail and a head. Okay, so
Sir,
let's assume that the head is hydrophilic, okay, and the tail is hydrophobic. Okay? So you can see this is the surface of water, and it will come like this, and then as you are squeezing it further, that it may order up like that. Okay, I mean that's a possibility. It's not as if that will happen. Okay, or if something chooses to be in the solid state, then maybe it will already come like this. Okay? You don't have to apply surface pressure to organize it. Okay, so effectively, what Langmuir said is that this is like really my gas equation. I mean, I can write it at a particular temperature. This is how pressure and volume varies. Now, he didn't actually take volume. He took surface area per molecule, which is kind of the same thing as the applied pressure. So obviously, if I've increased my pressure, then area per molecule will reduce. Okay, so by analogy, that's what it's like a gas equation. Okay? And we know that at higher temperatures, the behavior will be more gas-like. Okay, in most of the things, and whereas as you start lowering the temperature, you can have transitions to a liquid state and subsequently to a solid state. Okay, and then there are some, okay, which at a particular temperature would straight away give you a solid like behavior, almost like a you can think of it as a sublimation, from a gas to a solid, or solid to a gas. Okay, so so that kind of behavior. Okay, I mean, so everything was by analogy with the behavior of gases. And just to show you, like this is for stearic acid. Okay, so as you come to a kind of, you increase the pressure this way, okay, so your area per molecule is going down, at one point you see a transition, okay. No, sorry, this is your surface pressure and this is the area per molecule, okay, and you see a kind of a transition in pressure, that there's a steep rise, in the pressure beyond the point. And then after that, when you try to bring the molecules still closer, what you see is that's where you are encountering like a Leonard Jones potential, where you are bringing things beyond the collision distance, the interacting distance, and so that there'll be a tremendous buildup of repulsion. Okay? And that's what happens, and so he was able to say, okay, that probably is getting organized. Now, what Langmuir did is something very, very interesting, where he was able to actually say whether something is like a gas or a liquid or a solid. Uh, and I was just wondering, and he did an extremely simple experiment, very, very simple things, okay, to say whether, especially to differentiate between liquid and solid states, and I was just wondering whether you can conceive of any experiment by which you might be able to differentiate, on the surface as you are kind of reducing the area per molecule, whether something is a liquid or a solid. You understood the question, huh?
No, no, sir. Can you repeat the
No,
question?
I'm just saying that you are seeing over here that he obviously did not see all these things, okay? And I'm just saying that, when he was kind of reducing the area per molecule, okay, and he was seeing, of course, certain phase transitions from these pressure rise, but as a corroborative evidence, okay, can you think of a simple experiment that you might be able to propose, let's say, to differentiate between a liquid state and a solid state? I mean, how do you know whether it's a liquid or solid? Well, what he did was, I mean, it's extremely simple, and he talks about it in his Nobel lecture. So let me read it out from here. The oil films observed on water may exist as two-dimensional solids, liquids, or gases. The film on water obtained from stearic acid, okay, is solid. And then he says, if it is compressed by a force of 10 times per centimeter exerted against the paper strip, this solidity is manifested if particles of talc are dusted onto the surface and the effects of air currents directed against the surface are watched. The talc particles do not move freely over the surface. That's what you would expect with a solid, right? If I dust some powder, very, very fine talc powder on a solid, I mean, obviously the powder is not going to move, right? It will remain where it got put. Right? Whereas, if it's a liquid, it can exhibit Brownian motion. So you will be actually able to see the talc particles darting around. Okay? I mean, I hope you can see, how smart these people were, and this kind of an extremely simple experiment. So he, at this point, would have probably seen a liquid state, okay? And here, he would have probably seen the transition to the solid state. Okay, and as I told you, I mean, many molecules, also intrinsically will appear in a solid state. They will self-assemble. They don't need to be pushed to assemble. Okay? So, and that's the typical behavior of matter. There are some which are solid, some which are prefer to be gases and some which prefer to be liquids at a particular temperature. Okay? So that's what it is. But again, Langmuir's greatness is that he could, go beyond qualitative understanding to more quantitative aspects. Okay? And that's what you all will find also very interesting, because I think that in your curriculum you would have been taught to quantify, right? So, like for example, when he did this, okay, those kinds of experiments that I showed you with different kinds of surfactants or oils, palmitic acid, stearic acid, uh, tristearine, oleic acid, cetyl palmitate. Okay, Um and what he found is that there are some, okay, which give you a very consistent surface area per molecule. Okay, so that's A, right? And you can see it's about maybe about 21. So he's put it in angstrom. Yeah. So if you put it in nanometer, it will be about 0.21 nanometer squared. Okay, so that kind of area. Okay, and it actually tallies reasonably well with the kind of area, let's say, you would have for some of these molecules if you do by today's technique, like you do a crystal structure. You can actually see what is the area per molecule. So that's what he figured out. Although their molecular weights were very different, so what he said is that these molecules, it must be that after all, if there's not much of a difference between stearic acid and uh, uh, some other palmitic acid, except for the chain length. So he said the head group would be comparable. Okay, so it's just that a longer thing will be sticking out in one case, and a relatively shorter thing will be sticking out in the other case. That's not going to change the area per molecule. Okay, so he found that. And so what he did was a very simple experiment, and I'll just show you the calculation. Okay, like he says, a solution of palmitic acid, molecular weight is given in benzene. It contains 4.24 gram per liter, and it took 0.0239 ml of this solution, put it on a surface of 500 centimeters squared. Okay, so obviously these are ones where it is, especially in some of these cases, it's self-assembling to the compact structure. Okay? And then he allows the benzene to evaporate. Okay, and it formed a film. And so you can work out the number of molecules per centimeter squared, because this is given. So I take 4.24 grams per liter. He has taken 0.0239 ml. So I divide by 1000 ml per liter. I divide by the molecular weight. Okay. I multiply by the Avogadro number, and I divide by 500 centimeters squared, 500. Okay, so I get my number of molecules per centimeter squared. Okay, and from this, he could calculate, okay, that the area comes to 0.21 nanometer squared, which is what these are. Okay, these values. Okay, some of them. And so it's remarkable, right, that by such simple experiments, he was able to really get a fundamental understanding of orientation. Because the only way in which I can get this is if I have got the head group sitting on the surface of the water and the rest of it sticking out. Right? But he also found that there were certain molecules, where there was deviation. Like, for example, if I take tristearine, okay, tristearic acid, which is Basically, you can think of it as glycerol with three stearic acid bound to it as esters. So it's tristearine. Okay. So here, obviously the width of the molecule will be more because there are three of these. Okay, and and you can see it's roughly three times. Okay, 66. So otherwise they are quite comparable. And you can understand why it is 66. But if you take oleic acid, for example, if you don't know all that, okay, and you take oleic acid molecular formula and stearic acid, they're quite comparable, except for the fact that there is an olefin, right? And now the interesting thing is that if you have an olefin, today we know, okay, that if I write the oleic acid structure, okay, uh, and so this is C, this is my oleic acid, okay, and what happens is you don't get a straight chain because oleic acid is actually a cis acid, okay. So there's a bending, right? And so obviously this will occupy more space. The area per molecule will be more, and and that's exactly what he got 46 this, whereas the kind of molecular formula is the same. So he was able to actually, in those days, without doing any crystal structure, he was actually able to understand the shapes and sizes of molecules, through these kinds of studies. It's just remarkable. Another thing is, you see, today, don't put yourself in today's situation. You must be able to go back to 1915, when nothing was known about these things, and ask, could I have conceived these things? So, for example, if you conceive some idea today, and which doesn't exist, maybe 30 years from now it will look obvious. Today it doesn't. So I think you must be able to appreciate these Nobel lectures from that point of view. Don't appreciate it from today's point of view. Yeah, I know what's so great about knowing I can do Langmuir logic. Who made Langmuir logic? It's these people. How? And it's really very, very interesting. Now after that, so he got the length, of these molecules. So from the length, like palmitic acid, stearic acid, okay, I know that the length in stearic acid will be a bit more than in the case of palmitic acid if it's straight, and that's exactly what he got. Okay? And that's really the way he did this. Now he also, was how did he work out the length? Okay, so basically he knew the bulk density of stearic acid. Let's say, okay, I know the molecular weight, and so I could get the volume, okay, from the density and mass, okay, and the Avogadro number. I can get the number of molecules, okay, and so divide that by the area, and then I can or I can get the volume of one molecule, and I know the area per molecule. I divide one by the other, and I'll get the length of the molecule. Okay, so that's what he did, and also he defined the square root of A, okay, as an important parameter, that if I take the length by square root of A, then I can actually see how much is the deviation from a spherical geometry of a molecule. So this is like the aspect ratio, okay, of a molecule that will be determined by the length by square root of A. So I hope you can see, the enormous cleverness behind all of this work. Now, as I told you, I did not really cover
Sir,
every aspect.
sir,
Uh,
There's
Yeah,
one doubt. Can you go
yeah,
to
yeah.
the previous slide? Sir, what is the the meaning of the last column, length per carbon?
The length. Yeah. So I know the number of carbons, right?
Yes, sir.
So I'm dividing by the this total length by the number of carbons, like 15. Okay. So I'll get my length per carbon.
Yes, sir. But why did we do that?
Yes, because we know, okay, that for example, you don't expect really your carbon-carbon bond length to change. Okay, right. So I mean, it was a measure, of the carbon-carbon. Your fundamental bond length between carbon and carbon should not change in a single bond. Should be roughly similar, right? Okay. But obviously, if you see a deviation, it is not because the fundamental distance is changing, but because, maybe the molecule is slanted this way. Okay. So it will appear shorter, and you might find that the length per carbon is looking smaller. You got it, no?
Yes, sir.
Okay. All right. So again, take yourself back to 1932 when Langmuir gave his lecture. And as I said, I mean, Langmuir's lecture is relatively a bit more dry. But he did demonstrate some humor. Even in his that lecture. And so I'm just reading out. That what he concluded from all the work that he did. Okay. In the structure of matter, there can be no fundamental distinction between chemical and physical forces. This is also very interesting. Looked at it differently. It has been customary to call a force chemical when it is more familiar to chemists, and to call the same force physical when the physicists discover an explanation of it. It's quite interesting the way he says that. And that's true. All of us tend to do it. I remember a course I took on organometallic chemistry, and the professor would say that, the only difference is between an organic chemist teaching it and an inorganic chemist is that an organic chemist will write a big organic molecule and put a M for the metal, and say this is M, okay, and it's coordinated to the metal. And if it's an inorganic chemist, we'll write the metal with the proper stereochemistry and the coordination sphere and everything, and might put the organic as an R and say, and this is your R group sticking out, it's R. And so it's not different. That's what he's trying to say, and we all do that. Be depending on where you are coming from. Okay, there are also usually no sharp dividing lines between attractive and repulsive forces, or between the various kinds of attractive or repulsive forces. Nevertheless, a recognition of various types of forces responsible for the stability of matter proves useful in classifying natural phenomena. Thus, in a qualitative way, we may consider the following types of forces. And then he talks about the Coulomb force and how it has a 1 over r squared dependence. Okay, and we know what are typically electrostatic interactions between a positive and a negative charge. And all those kinds of molecules like sodium chloride, etc., and how they are held together. Okay, and then he uh, found out about dipole forces, okay, and which depend on orientation of the dipole, and it has a 1 over r to the power 4 dependence. Then he talked about the valence force, which is the sharing of atoms, the electrons in the two atoms, okay, and it was very important because of things like tungsten oxide, which was clearly a kind of a chemical bond. Okay. And then he talks about the van der Waals interactions, which are specifically related to polarizability. How polarizable is a molecule? Okay, and typically the attraction is 1 over r to the power 7 dependence. So these various orders, by which their interaction can change, in terms of the distance scale, became clear. And then he was able to look at the repulsive forces, especially between molecules or atoms which have got a complete octet, and there, if you're trying to push them together, then of course there will be a lot of repulsion beyond a point, and so he then understood the repulsive forces. Okay, and then he also talked about counterbalancing forces, like obviously if I have got an attraction between let's say a positive and a negative charge in a solid, but the two don't collapse, into completely. All right, you still have a separation. Okay, like for example, that counterbalancing in a solid compound actually comes from the electron gas or the Fermi level in the solid, where exactly the conduction and valence bands lie, and the Fermi level lies, and so that is kind of what he talks about is a gas pressure, which is exerted, which actually prevents the complete collapsing of the positive and negative entities. This was the way. After today, after quantum mechanics, these things are explained a bit better. But nonetheless, I think that it's significant that he was able to come up with these. Okay. Now, I was just trying to see, like I did the last time, that what are the lessons, which Langmuir's Nobel lecture. I should have actually put Nobel lecture plus some of his papers, which I studied and which I will share with you. That what can we learn? Because at the end of them, I want you all to become like Haber or Langmuir. That's what I want you to do. I want each one of you to become great, and not just a student of Langmuir or Haber. I want you to become like this. Okay, so first is, like what we learned from the Pasteur's quadrant. Like Pasteur, he identified important problems of practical interest. Okay, and then in solving them, he laid out a field of science, and that's exactly what Langmuir did too. The problem was, I wanted to increase, the electron emission from tungsten. I wanted to increase the incandescence of the bulb so that it gives more light. That's the fundamental problem. And in trying to solve them, just look what he found. He opened up new areas of science. Even today we talk about those. Nothing has got obsolete. So that's the greatness, of people like Langmuir and Pasteur. Second, availability of special equipment. Had he not had, that kind of a system which industries had to offer with a very high vacuum and an equally great pressure gauge, with which you could measure, extremely low kind of changes in the vacuum level, and correlate that with adsorption or desorption. He would not have been able to do it. So obviously, special equipment, just like Haber had his high pressure equipment, that's what he had. Or Ertl had his surface spectroscopy equipment. He had a special equipment. What Langmuir, to me, it seems stands out compared to even all the others, is he had an outstanding grasp of fundamentals, okay? And which you all are very good at. Your many of you, your fundamentals are very good. Okay, and he used those fundamental understanding and knowledge, to actually design experiments. So that was brilliant. The way his understanding, like he says, no, the rate of arrival of molecules, and the mean free path and the correlation, and looking at that the temperature of the glass bulb would have got equilibrated, so it's fantastic, so that's the kind of thing he did. Okay? Ability to generalize, you saw in the last slide, that he could classify various forces. I wish I could have gone through the entire lecture. Okay? But that, all the way from what is a Coulombic interaction, to a dipole interaction and a polarizability related interaction to the counterbalancing forces, he was able to envision and classify forces. There's nothing more fundamental than that. Okay? And the ability, like Van Top, to be able to draw analogies. Look at how people have exploited the gas equation PV is equal to nRT, and how they are able to say, okay, I'll show it as pi A is equal to nkt, or pi V is equal to CRT, and lucid articulation compared to, although I will say I found it a bit dry, his Nobel lecture, but then, the subject matter was sufficiently complex that even in that he was able to get across, and someone like me who's any times 1,000 times less competent than he is, and that I could still understand at least bits and pieces of it, it means that the articulation was reasonably good. Yeah? So he had that kind of an ability. Okay. uh, and by the way, these are only thoughts that have come to my mind. Uh, You might want to add to this list or subtract from this. If you say, no, I don't agree, I didn't see this, it's up to you. I mean, these are just impressions that the lecture created on me. Okay. Any questions from anyone before we move on? All clear?
Yes, sir, no
Everybody
doubt.
understood?
Yes.
Yes, sir.
Okay, because if you don't understand the lecture, then of course you won't be able to appreciate it. And I urge you to read it. Because what has happened is most of us have stopped reading primary literature. We always are reading derivative things, which is passed down by others. And there's nothing as nice as listening to it from the horse's mouth.